So let's see, so one thing we need to do is talk about stable normal bundles and inverse bundles and smoothing, or how to put a smooth or a cat structure on our manifold across some high dimensional Euclidean space. So let's start with inverse bundles. So if we're given a top bundle over space X, it doesn't have to be a manifold. So if we're given a top bundle, let's call it C, of, let's say, dimensions, fiber dimension n, there exists an inverse bundle, eta, of some dimension, such that Cn plus the Whitney sum of eta is equal to, let's give this a dimension, m, is equal to the trivial n plus m bundle. So that's what's meant by an inverse bundle, of course. So how does this go? Well, so first, the first step is to assume C is trivial over, say, U1 and over U2. So then, well, maybe before that I should say, so before this, X is paracompact. So X has a finite cover U1 up to, let's say, UR with C restricted to each UR trivial. So each of these U's may consist of lots of open sets. They're probably not connected. Well, if it's a compact, if X is compact, then you can choose a finite number. But if not, then paracompactness is you can find a locally finite cover, and then you put them all together. This comes from covering dimension. Oh, I don't know, what does it come from? Anyway, we've got that. And then C is determined by its touching functions. Functions hij, mapping ui intersect uj into top n. This is the homeomorphisms. Maybe fixing the origin, might as well. So it just tells you how you glue together the fibers over these two when they overlap. Okay, so that's a comment I should have made first. Now we've got C is trivial over U1 and U2. And on the intersection, there's a clutching function joining them. Well then, construct our normal bundle over U1 union U2 as follows. So just use the inverse. Use, so make U trivial over each of U1 and U2, and use, let's say, call it G, Ij, equal to Hij inverse. So you just glue together the, I'll make it trivial of rank n, rank n, so that this makes sense. So that's so over these, the normal bundle is going to, the inverse bundle is going to be Rn bundle also, and so then you can glue together by using the inverse functions. Well, it takes a little bit of thought to see why that works. And so what you need is you need a homotopy taking xy to minus yx. You need to be able to rotate 90 degrees. Is that what I want? I think that's what I want. Let's see if that works. So homotopy lambda t. This is mapping Rn cross Rn cross Rn. So you just, these are vectors, and so you're just switching factors. You know, see, there's two factors, it's a 90-degree rotation. So now, I want to claim that we have a bundle, over x cross I, we have a bundle over x cross I, and at one end, and so what is this bundle? Well, what I claim is, at one end, it is trivial, and at the other, it is C plus nu. Thereby showing you've got that nu on the union, and this overlap really is an inverse bundle because T gets something trivial. And why is that? Well, you can sort of see why, because so how did I build this bundle? Well, so I built the bundle by using, let's see, so I have to say what the clutching functions are. So I think I'm going to use something like lambda t. Well, I better just put it right when we copy it down. I want lambda t, so inverse composed with the identity cross G it's my notation, I have to remember the notation here. Identity cross G will basically be composed with lambda t composed with H cross the identity. H of there's G, and the G in nature is over here. And so the point is that when if t is equal to 0, so that lambda 0 equals the identity, then you get C plus nu. Because when the first, so you're applying this to a pair of vectors x and y. And so first of all, you rotate x by h. This is the identity, and you rotate y by g, and that gives you these two. Because here you're gluing fibers. When you go from U1 to U2, you're gluing by h, and here you're gluing by g. So that just gives you this bundle. But z equals 1, so that lambda 1 is switching x and y. So lambda 1 of xy equals whatever it was, minus yx. Then you're switching the factors. So here you first apply, what's it going to do to x? Well, it's going to apply h, and then it's going to switch x over to the second factor, and you're going to apply g. Oh, I should put an inverse in somewhere.
I think that is Atiyah who first used this trick.
Is it to you? Well, it goes earlier. I
Maybe
think.
even earlier, yes.
Probably even earlier.
Yeah.
And then you apply g, which is h inverse, and so that just undoes it. And so that's why you get the trivial one. So you just, and then in between it's some other bundle, and then in between it's a bundle, whatever it is. And then you're using the fact that over an interval, the bundle has to be the bundle at one end cross I. And so that's why the two bundles are the same. So just a little trick like that. Now then, well, so now you might figure, well, let's just go ahead and do this. So now we've got U1 union U2, and we have this inverse bundle here. And now let's pick our next open set U3 and do the same thing. Well, this doesn't work. It doesn't work, and let me explain, those of you who haven't seen such things before, let me explain why. So let's just take RP2 and think about trying to find an inverse bundle to RP2. Well, or if you've had characteristic classes, remember that the characteristic classes for this, so the total Stiefel-Whitney class of the tangent bundle of RPN, the total Stiefel-Whitney class is 1 plus alpha to the nth, where alpha is the first homology, or it's a generator of RPN, is the two coefficients sufficient. And so it's really just a circle. And if n is 2, it's just it's got the Mobius strip around it, and it's non-trivial, and so on. So then you take this and write it out, and you'll get lots of non-trivial. You get lots of non-trivial entries in there. Every time you get an odd entry. So this is quite non-trivial. However, for what we were doing here, if we just took these two, if you just take these two, if these two just gave you that circle, and you looked at the tangent bundle over that circle, it would have would be like a Mobius band. And you can find an inverse bundle for that if you just choose the Mobius band itself, because you put two Mobius bands together, you get the trivial bundle. So you'd have a one-dimensional inverse bundle. Well, then just continue the argument, if you could, and you just keep on making a one-dimensional inverse bundle. But the inverse bundle to this has got to be the inverse of this cohomology class, which is certainly not one-dimensional. So this implies the inverse bundle is not one-dimensional. But it looks like if you just apply this argument as we were doing here, well, see, I'm not saying this quite right. But if you did it for just n equals 2, you'll find out this goes wrong. And the reason is that the same argument does not satisfy the cocycle condition. Because if you have your open sets that look like this, U1, U2, U3, then take a fiber in the middle here. You're gluing together, because it's in U1, U2, you take their fibers and glue together by something. And then when you glue U3 on, that's glued on by something, but that has to be glued on by the same element as when you glue U1 to U3. That's what's called this cocycle condition. So in other words, if you take the fiber over this, say Rn, then H12 followed by H2, followed by H23, applied to a vector in Rn has to be equal to H13 like that. You gotta do the same, you gotta glue the same way. And so this is the cocycle condition. This does not necessarily follow if you just take this argument. And the reason it doesn't follow is basically because if this is true, well, what you need is that H23 inverse, H12 inverse equals H13 inverse, and this is not necessarily true. You need something like that. So you need a different argument. It's not quite as easy. This works fine for just two of them, because you don't run into this cocycle condition, but it doesn't work for more. So you need to use a more trickier argument. So what we need is, so go back to these three, to having three of these. So you've got new over here, you of course got new here, you have new here, you also have C here over this, and of course you have C over that. So what we need, so how you can consider V equal the intersection of U1 union U2 with U3. So call that open set V. And what we need, let's see what we need. We need a bundle. Now we'd like to apply this argument to these two. There's a pair of open sets, and never mind that this is the union of two. We'd like to apply this argument to these two open sets. So we need a bundle which is trivial on V and has an inverse over, let's see what we need here. Make sure I get this right. So this would be a bundle which need a bundle, call it lambda, over all three of them, over U1 union U2 and U3. So this is like our original bundle C, which was defined over each of these, the union, defined everywhere. So we need a bundle which is defined over all three of them, such that C plus lambda is trivial over U1 union U2. So it's going to be trivial over that. and over U3. So if you have a bundle which is trivial over each of these two, then this argument gives us an inverse. Because all we assumed in that argument was that we had this bundle C that was trivial on both U1 and U2, and we got an inverse then over the union. So if we find a bundle lambda such that this is trivial over both, then there exists an inverse U, that's our inverse bundle U, such that this bundle, C plus lambda, Whitney sum mu is trivial. In other words, by what we just did, we found an inverse bundle for this bundle. But what's this bundle? Well, this bundle is also C plus a bundle lambda plus mu. When you take Whitney sums, you can put the parentheses in either place. And so now, there's our inverse bundle. That's our inverse bundle over all three of them. So what we're after is this bundle. So we want a bundle which is trivial over both of them. Well, so what should that bundle be? So C, C restricted to V is trivial, because V is inside these charts where C is trivial. So that's trivial, that's obvious. And C plus eta restricted to V that's C over V is trivial, so this is the same as just a trivial bundle plus mu restricted to V, just because C is trivial there. And since this bundle is trivial on V, so this bundle, well, that both bundles, so this extends trivially over U3. I mean, if you've got a bundle, the intersection that we're talking about here is this stuff. That's a V. U1 union U2 intersected with U3. That's what V is. So what we're interested in is this, but if this is trivial, we found a bundle which is trivial, so you just extend it trivially. Trivial bundles extend. So there's our bundle that we wanted a bundle which is trivial over U1, U2. Well, that's true because this was our this U was our inverse bundle to C over U1 union U2. So this is trivial over that. And it's trivial over U3 just by this extension. Because when you restrict a V, it's trivial, so you just extend it. So it's trivial over U3. So it satisfies both of those. Therefore, it has an inverse. So that's trivial, but by rearranging, you get your normal bundle. So notice that the normal bundle climbs in dimension. At first, the normal bundle was that what we did was we picked lambda to be new. But now the normal bundle is higher dimension. This was n-dimensional, but now we've picked something new, and so the dimension's gone up. So the dimension of the normal bundle keeps going up as you bring in more charts. So an inductive hypothesis just finishes the proof.
Why is the first statement on the second chord the case?
This statement?
Yeah.
Because V is the intersection, remember. Our bundle C is trivial over these charts, so the intersection is inside one of the charts and therefore trivial.
Okay.
But that's why V is small. V is a small thing inside U3, so that's why it's trivial.
Is this very much harder than the argument that vector bundles have inverses?
No?
It's the same.
Well, because of this. This is
No,
this
but
is
I
a
mean,
statement for
sure,
smooth
but
bundles.
the same problem arises for vector bundles. I mean,
Yeah,
this
yeah,
I mean, are you doing something specifically in the topological category, or is it
No, I think, well,
not really? I mean, you won't have the same difficulty in this direct approach for vector bundles.
I know it's a long time since I've thought about it for vector bundles, but I'm not sure. Just because of this fact here, you know that.
Yes, but if
you
one
see,
wants...
every time when you build RPN, you start off with covering the circle, and then you add another chart to cover the 2-cell, another chart for the 3. Every time you do that, the dimension of the inverse bundle has to go up.
I understand
So
that.
it's something like this has to.
But you have the same problem in vector bundles.
Yeah, yeah.
That's what I'm
You
saying.
have the
Really.
same problem with vector bundles, right?
Yeah.
Because of this,
Yeah.
this
Oh,
statement
of
about
course.
this, there's two classes. Yeah.
How did the inductive argument finish this?
What?
Pass up, compact?
Well, the Perkupak says you have a locally finite subcover. So it's locally finite, so well, let's see, do you need covering dimension?
Does it need partitions of unity or something like that? Something.
If you have a space, like manifolds have covering dimension m, which means that you could use m+1 of these things, and they're all lots of different pieces. Like think of a triangulation. And so one set is all the neighborhoods of the vertices, and the next set is all the neighborhoods of the barycenter of the one simplices. And you keep on going. And so there are lots of different pieces, but it's trivial over each one. Now, you're testing my memory of parent and companions. I kind
Let's
of think
stick
we can do
to
the same thing, but I'm not sure. Anyway, I really want this for manifolds where you can do it because of covering dimension. Okay. Now, let's see, the next step is to get stable normal bundles. So this was inverse bundles. Now we want stable normal bundles. So suppose we've got M, dimension M, embedded in Q of dimension Q. So this is an embedding. Say, give it a name, I for the moment. And this is to imply there exists a normal bundle when you, for M into Q, but then into Q cross R, say some large S, so that this has a normal bundle. It may not, if you just embed it into Q. You don't always, even a locally flat, actually I don't care whether this is locally flat, but even if it were locally flat, you might not have a normal bundle. But if you stabilize, then you do. So this is one of these sort of tricks. I don't know version of it must go back a long time. But anyway, we want to do this with a picture. So this is M, and this is Q. They're both one-dimensional, unfortunately. And now you have M. Yeah, M embedded in Q. So the first thing we want to do is look at the graph of M and Q. And since it's an embedding, let's make it a little bit longer. It looks something like this. It looks monotone when you take the graph. So this is the graph of M inside M cross Q. Now, Q, so M is an ANR. So there's this neighborhood of I of M, comma U, which we might as well take to be Q, because if it isn't all of Q, just throw away the rest. So throw away some of Q, so that's that. And a retraction R from Q down to M. It's really a neighborhood of M, but might as well be all of Q for our purposes. So now you have this retraction, and we can look at the graph of that. So again, the graph of this map also sits inside M cross Q or Q cross M. They both sit in the same space. Now, it's a retraction, so the graph looks just the same on M. So we're retracting Q, it looks just the same there, but then the rest of it goes off somewhere. And it's not monotone, it's monotone on this part, but on the rest, you're mapping a higher dimensional thing into M, so there's lots of point inverses. Like this point has 2 point inverses when you think of mapping Q into M. So it's not monotone, but there it is. Now these things have normal micro, so there's a couple of bundles around here. So for I of M, you've got a bundle which runs this, in the right color. So this is the thing, you have a point here, and so there's a neighborhood back here. Anyway, there's a bundle that goes this way, and I'll put this in white. And what is this? What is this? Well, for each point, you've got a coordinate chart in M. So that gives you a coordinate chart there. And these coordinate charts move around. They're not homeomorphisms, they move around, they just overlap like this. But we've already been through this theorem of Keister's, which says that you can find inside a microbundle, you can find a bundle. So inside there is actually a bundle. And this involved, and we're just going to remind you that if it looks like this, well, you actually throw away the lower part here, so it's just an embedding, and then you expand the embedding out. And that kind of an argument will give you a bundle inside there. So there's a bundle inside there, which we'll call, I don't know, we'll call it
K for Keister.
801, yeah, 801. But then there's also a bundle the other way. So for all of the white stuff, for Q, so if you're looking at Q, the Q is what's got. So Q's got this bundle. M has a bundle going the other way. And since that's an embedding, in monotone, you can actually have a bundle both ways. So now, what does this picture tell us? Well, it says that, M, or I of M, has a normal bundle in Q cross M. It had a bundle, doesn't in Q, but if you cross with M, it has a normal bundle, and it's, which one is it? It's, I guess it's the red one. Let's see, I didn't, so the white one is that, the red one is eta 2. Normal bundle eta 2 is the normal bundle it has in here. Because that's, yeah, the red one is this way, so it's a Q-plane bundle. Because it's coming from coordinate charts in Q. So eta 2 is a, I should keep my colors consistent. That's a Q-plane bundle. And mu1 is an M-plane bundle. Well, if the tangent bundle to M were trivial, then this is in Q cross RM, and we're done. We have a stable normal. So if the tangent bundle of M is trivial, then this is equal to Q cross RM, and we're done. But it might not be trivial, but if not, aha, we have a normal bundle. If not, connect some, a wiki sum, with the inverse bundle to tangent bundle M. So that's why we prove the inverse bundle theorem. So when you do that, then that will give you something, will give you a trivial bundle here, and you have a. So, but when you're doing this, you're really tacking on another bundle coming out of the board. So you're adding some fibers. Let's see, the red is the tangent bundle. No. What's this tangent bundle of M is showing up as the white bundle. So you see these fibers are coming from the coordinate charts in M. If those can all be chosen trivially, then that white bundle can be chosen trivially. But if it isn't trivial, then to this white bundle we add its inverse bundle going out this way, and that gives us a trivial bundle. But when you add this bundle, a bundle over a bundle is still a bundle. And so you have this larger bundle projects down onto the white bundle and then down onto M, so that you get a trivial bundle. So the adding inverse bundle is how you do this. So somehow you can take an embedding, which doesn't even have to be locally flat. It can be a wild embedding, it can be almost anything. But when you add enough factors, you end up with a normal bundle. Okay, well, I guess I only have a minute or two left. So let me just say one thing I've said before, and then we're done. And that one thing is that yes, so now we want to put a cat structure on M cross RS. If the bundle map from M into the top, and this classifies the tangent bundle. So, and if that tangent bundle, or normal bundle, anyway, whichever. And here you have V cat, and if it lifts, so if there exists a lift, if and only if there's a lift. So if we can lift, and that was a cohomological condition. So if you can lift, then how do we get the structure on M cross RS? Well, you really replace M by, so M, you put M inside some high dimensional Euclidean space, I don't know, RL. And then with a normal bundle. So do that. And now you have a neighborhood, so then you have M across, well, you have the neighborhood, which is the total space of this bundle. So that total space sits inside RL, so this is cat, because it sits inside RL. So therefore it's, it's an open set inside a smooth manifold. And so this, but this also just retracts down to M itself. So if you have a map of M in here, you have a map of the neighborhood in here, and then we have a lift, and now we can ask that that lift be a smooth map. So cat, return this lift lambda, return lambda to a smooth cat embedding of this normal bundle into the cat. So the smooth case, this is a grass mine. This is a finite dimensional smooth manifold. So this is could be, and we're talking about a map from the smooth manifold, namely this normal bundle into a smooth manifold. So we approximate it to a smooth map. And then this puts a cat structure on.
Well, cat is PL or smooth.
PL or diff. Cat structure on, well, let's see, it's supposed to put it on M cross R, S for some S. So let's see where. I guess I probably wanted to classify the normal bundle here. The stable normal bundle. Let's find this bundle. Because then you have the tangent bundle of M plus the normal bundle. That's what gives you the RS. Total space, the normal bundle plus the tangent bundle. Anyway, I have to stop, so that's how you get to a cat structure here, then you use a product structure theorem, you do all the rest of the stuff, and thank you very much for listening.
Thank you very much. Should all come in front, please. In front of the camera.
You know you had to do this, huh?
Oh, yes. The camera is...
So, yeah,
Yeah,
there's
you
the camera.
So thank you very much, Robin. We brought you
I
some...
don't know why you brought me something, but
Well,
that's
it's not
very
just
nice.
anything, it's something
Not just-
rather...
So I should open it.
Yes,
Yes,
you can
okay.
look at it anyway.
I can look at it.
The
Well,
card,
first
the card.
I-
Wishing you all the best of luck for the book.
Why do I need lots
This is
of-
only the beginning, this is not the end.
This is good, this is good, this is good, I'm glad to have all your signatures, yes. And then I should open this, huh?
Yes, it is.
This is gonna help you write the book?
Yes,
Oh, it is. Well,
definitely.
It's definitely what I need most,
Absolutely.
is help. Of course, you know, Carmen was doing all the figures, so there's
Yeah.
a great deal of.
This will not be good for your figure.
Oh, I see, it's gonna help me write the book, but not. In that case, you guys, let's see. You have to help, you have to help with, anybody want some chocolate?
No, it's for you, no, you need to be strengthened. You need to be, keep your strength up.
Turkish coffee?
Oh yes, very appropriate Turkish
Oh,
coffee
yes,
for
with
this.
the art-
Ah, very.
And, yes, raspberry, maple pecan, and the chieftain. Ah, that's
That's
very appropriate also.
Chieftain's haggis flavored.
This looks to me like a large,
It's a mandala, yes.
Yeah, like a large link.
Yes. From
Okay.
the chocolate tree.
Well, thank you all. Thank you for listening. Thank you, Carmen, for so many things. Andrew, for arranging this. Yes, all of you.
Okay,
Okay, good,
okay, that's it.
good. Good.
Goodbye.
Goodbye.
You'll get something.